Welcome back. So now we want to finish off our unit on one-dimensional motion by spending some time working with the kinematic equations. But before we get into the kinematic equations, we do want to remember that we want to be able to solve these problems intuitively. So once we start using the equations, it becomes tempting just to plug numbers into letters, and really anybody can do that. The question is, do you understand why you're doing what you're doing? So to start with, we want to work out a problem, but we want to do it intuitively. Then we're going to go through the equations, and then we're going to do it using the equations to solve the problem. So to start with, we have a car that is traveling at 20 meters per second, and we want to know what is your stopping distance if the acceleration is negative 5 meters per second squared. So to solve a problem like this, it's often a good idea to draw a little sketch here. So there's your terrible looking car, and so it is traveling to the right, and so at the beginning it is traveling at 20 meters per second, and eventually it comes to a stop. So when that happens, that means that the velocity is 0 meters per second. So we would like to know how long it travels from here to the 20 meters per second to where it stops. So how do we do that? Well, if we think about this, we know that the initial velocity is 20 meters per second, and the final velocity is 0 meters per second. So that means that the average over this run is going to be 10 meters per second. So if we just know the time, we can multiply 10 meters per second by the time, and then we get the distance, right? Velocity times time, or average velocity times time, gives us the distance. So that means we want to know how long it took. Well, at the beginning, our velocity is 20 meters per second, and after 1 second, the acceleration is negative 5 meters per second squared. So after 1 second, our new velocity is 15 meters per second. After 2, it is 10 meters per second. After 3, it is 5. And after 4, it is 0 meters per second. So it takes us 4 seconds to come to a stop. And that means if we're traveling 10 meters per second for 4 seconds, that means the distance that we travel is 40 meters. Okay, so I think we've tried to do it more intuitively up until now, where rather than focusing on equations, we've tried to sort of think about what this stuff means. But next we're going to go through the kinematic equations and then look at our strategies for solving these problems using the kinematic equations. Okay, so we did that last problem in an intuitive way, but a lot of you are going to want to use the equations, especially when the numbers don't work out quite so easily. So to solve these types of problems, we're going to have 4 equations that we're generally going to use to solve for one-dimensional motion. So our first equation here, so this is the velocity is equal to the initial velocity, so v naught, so that means the initial velocity, plus the acceleration times time. So that means that this is really just the definition of constant acceleration in the form of equation, right? The change in velocity is the acceleration times time. So acceleration times time gives you the change in velocity. The second equation here, so this is for finding the change in position when you know the initial velocity and the acceleration. So here we have delta x, so this is our change in position, and this is equal to the initial velocity times the time, plus 1/2 the acceleration that our object is undergoing, times the time squared. So this is a really common equation in free fall problems, right? So you have a falling object where you've thrown it up into the air, because the acceleration here, so the acceleration in the free fall problems are going to be your negative 10 meters per second squared, right? Your acceleration by gravity, and so then your initial velocity is going to be how hard do you throw the ball. And so then if you know those two things, right, then you can figure out at any given time what is the change in the position. So this is really useful for those free fall problems. Our third equation here, this is really a combination. So you'll notice this first part here, 1/2 the v naught, or the initial velocity, plus the final velocity. So this is just your average velocity, right? This is initial velocity plus final velocity over 2. This is really the same thing. Then you multiply that times time to get the change in position. So this is really the thing that we just did, right? The average velocity times time gives us the displacement. It's what we did in this stopping distance question. And then our last one here, so this is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position. So this equation is mostly useful for some of the more complex free fall problems. So here, if you know the initial velocity and you know the change in height, right? So if you are, I don't know, throwing a ball up in the air off of a cliff, for example, then if you know the change in the height, or this delta x, the change in position, then you can find the change in the velocity, or at least if you know the initial velocity, then you can find the final velocity. Okay, so these are these equations. So basically, we're going to now work a couple problems using this, and we'll do that next. All right, we're going to try this problem again, this time using the kinematic equations. So one thing you often want to do for this is you want to write down what information you have. So your initial velocity here is 20 meters per second. So we know that. We know our acceleration is -5 meters per second squared. And then we know we're looking for the stopping distance. So that means our final velocity is 0 meters per second. So those are the big pieces of information that we have. And so then what we want to do is we want to find what is the stopping distance. So what is the change in position during this time? So probably the logical formula to find the change in position, so that is this formula. So delta x is equal to 1/2 v naught plus v times t. So that, unfortunately, we do not know the time. So we want to know what the time is first, and if we know the time, then we can solve for the displacement. So to solve for the time, what we can use is we can use our formula for the change in velocity. So the final velocity is equal to the initial velocity plus the acceleration times time. So our final velocity is 0 meters per second. Our initial is 20 meters per second. And then our acceleration is -5 meters per second squared times t. And so then we add 5 meters per second squared to both sides. So this becomes 5t is equal to 20. And that means that t is equal to 4 seconds. So now we know the time, so we can add that to what we know. And so then we can plug into this formula for the change in position. So that means this becomes 1/2 times v naught, so 20 meters per second, plus 0 times 4 seconds. So this becomes 10 times 4, so this becomes 40 meters. So notice, we got exactly the same question that we got last time. It's just this time we used the formulas rather than doing it intuitively. The next question I want to do is the acceleration of a car problem. So this is another one that we're going to do using the formulas. So in this case, again, we're going to want to write down what we know. So what do we know here? So we've got a 1,000 kilogram racing car, so it's accelerated from rest at a constant rate, and it covers a distance of 125 meters in 5 seconds. So we want to find the acceleration. Well, what do we know? We know delta x, so the change in position is 125 meters. The time here is 5 seconds. And so, and then we know that the initial velocity, so v naught, is 0 meters per second squared. So here, we're going to look through our formulas again and see what we can solve for. So if we look at the kinematic equations, we have this second formula. So delta x is equal to v naught t plus 1/2 at squared. And so if we look at this, we know the initial velocity, that's 0. We know time, so time we need 2 places. We don't know acceleration, but we do know the displacement. So that means we know everything except for the acceleration in this formula. So that means we can then solve for the acceleration. So our change in position is 125 meters. V naught is 0. So that just goes to 0. This becomes 1/2 a times the time, which is 5 squared. So that becomes 25. So now we can just do some algebra to solve this. So this becomes 1/2 a times 25. So this becomes what? 250 divided by 25. So this becomes 10. And so then our acceleration here is equal to 10 meters per second squared. Okay, so that's how we do this kind of thing. So you've got a couple of these to do. You also can do it more intuitively just by coming up with the average velocity, doubling it to get the final velocity, and then dividing by time. Either of these will work, but that's the basic idea. All right, so good luck with your questions.